All right, so yeah, I'll be talking about using a random forest to generate cloud-to-ground lightning probabilities. So lightning is a pretty big hazard, but currently in the National Weather Service, there are no lightning alerts or warnings issued for lightning. However, on average, lightning actually kills more people than tornadoes each year. Forecasters are also consistently asked by emergency managers to provide decision support services for lightning, whether it's for outdoor events, fairs going on, sporting events. So the main goal was to create an automated probability for a storm that it was going to produce cloud-to-ground lightning in the next 30 minutes. So looking at our data set, I looked at storms from June of 2014 through June of 2015. We used randomly selected 3 set days, where we started at 12 ZN day 1 and went till 12 ZN day 3. 3/4 of our data were used for the training data set, and then the other quarter was for our validation. We did this CONUS-wide, and we used the VISLA cloud-to-ground lightning, Earth Networks in-cloud lightning, and the RAP near-storm environment model data, and then the multi-radar, multi-sensor, or MRMS severe product suite. So here's just a list of all the products that we looked at based on which groups they fell in. So for a random forest data set, we used enhanced k-means watershed technique, and we were able to track storms over time using the MRMS reflectivity at -10 degrees Celsius. And in order for it to be considered a storm, we needed a minimum reflectivity of 20 dBz, and then we looked at 3 scales, 200, 600, and 1,000 kilometers squared. So what we got from that were these tracked objects, and then we were able to create a temporal data set for each of these storms based on the MRMS model and lightning attributes. So this is just one subset, but essentially for each time step, we would get a table where each row was a different storm, and it had the associated attributes for that storm. So for a trained data set, we needed to find the answer, so we had to mark whether or not, we had to look into the future to see if there was lightning that actually occurred with this storm, and we added that to the table. So now we can get into what is a random forest. We start with a trained data set where we have all of our features and then the answer. Then random subsets are created. This is where the random comes from. So random rows and columns are selected to create these subsets, and those subsets also contain the answer. So in this case, each color represents a different subset. From there, each subset then creates a decision tree based off of those features. All of these trees are your forest. So once we have all these trees, we can run our validation data set through. So each storm would go through each decision tree and get either a yes or no answer whether or not cloud-to-ground lightning occurred. And then our probability was the number of yeses over the total number of trees. I used Python to do this. There's a random forest classifier module. For the specific case, I used 300 trees, and the max depth was 6, so it could go keep splitting down to up to 6 times. So looking at some of the results, here's a reliability diagram. On the y-axis, we have the observed relevant frequency, and then on the x-axis, we have the forecasted probability. The dashed black line is kind of the 1-to-1, so that's your ideal perfect world. The red line here is the random forest, and then we also ran this through a logistic regression just to compare. And then we have a histogram here that shows the number of storms and which probability bins that they were binned up into. And so here we had a Brier skill score of 0.793. So then we looked at, what if we looked at just total lightning? We took away the MRMS and model data. And you can see there's a little bit more under forecasting, and the Brier score dropped to about 0.78. We then looked at, what if we took out lightning? A lot of times some of the lightning networks will drop out. How well does that do? But the Brier skill score dropped even more to 0.691 for that case. One of the really cool things about random forests is it can tell you which features are the most important. And so for the case where we used all of the data, the most important features were the in-cloud and cloud-to-ground lightning features, which kind of makes sense. If it's already producing lightning, it's probably going to continue. You can see when we took out lightning, it was the MRMS products that were the most important. So we started with these 28, and so based on which were the most important, we cut that down to 18. And so we decided to look at how well that did. Essentially the same compared to the 28. So it's a lot more computationally easier to only track 18 versus 28 objects or features. So then we decided, do we want to split this out by region? Western region has a little bit separate or different types of storms than, let's say, the Central Plains. So we did this based on the CWA and which region it was in based on the Weather Service. Looking at the feature importance for each, again, it was the lightning, no matter which region you were in. And then the blue table shows the number of storms that went into each of these regions. So since the cloud to ground 15-minute was the most important, this plot shows the frequency, or basically the number of storms on the y-axis, and then the x-axis shows the actual cloud to ground flashes for that 15 minutes for a storm. So the kind of blue turquoise line here is the western region, and so you can see that that maxes out at about 400 flashes, where the rest of the regions are kind of off the charts. So we looked at this for all of the lightning, and western region definitely was less active with lightning, and then eastern region was a little bit lower as well. Central and southern were pretty similar. So we kind of hypothesized that, hey, splitting this out might look a lot better. But when looking at, when plotting up the reliability diagrams and looking at the Brier skill scores, they actually all decreased. We need to do a little more investigation to this. We don't know if it's just we didn't have enough storms that we input, or if there just really isn't much that can be said about splitting them up. So what I'd said originally in the beginning was that we want to use this in real time. So we created a new algorithm using the probability trees that we got. And so we were able to display, these are two automated objects, and then with their probabilities associated with them. And if you click on the lightning or on the objects, you can get a time series of what either the lightning or any of the features that we tracked, what they looked like in the past. And so for the past 2 years, we actually brought in National Weather Service forecasters, and they use this product in the probabilistic hazard information experiment that takes place in the hazardous weather testbed in Norman to actually take over and issue these probabilistic lightning hazards. And those lightning hazards then went to emergency managers that were also as part of the testbed. And both emergency managers and forecasters responded very positively to this product. Emergency managers really wanted this immediately because they don't even have, a lot of them don't even have access to the VISLA or Earth Network's lightning data. So some type of probabilistic lightning was something that they really would like. So in summary, more data isn't always better. It can slow down processing, and not all of it's important. And rainforest can easily take that large data set to create these decision trees, and it tells you which features were the most important to go into creating those. For a probability of lightning, we had a very high Brier skill score, 0.792, and we combined everything. We broke it out by region, but that may not be the best. Some of our future work, we want to test this on smaller scales, or start tracking at about 20 kilometers, since we did miss quite a few storms of that popcorn convection, but that still did have lightning. Once GO 16 has been up in the air for a while, and we've been able to collect a year or two's worth of data, we can incorporate the geostation lightning mapper, so we can get more lightning data, as well as other satellite products. And then our goal is to eventually push this into the National Weather Service operations. Thank you.
Now we have time for a few questions. Okay.
For your skill scores, did you use the out-of-bag estimates from futures you cross validation?
Away cross validation.
Yeah, futures with the out-of-bag.
Okay.
That's a really nice presentation. Thank you. Is this on?
Yes.
Okay. I'm wondering if you've considered comparing your results or training your results with the lightning mapping array, which is a research lightning network, because I think sometimes the CONUS-wide lightning detection systems, they're really great, but they have sort of variable detection efficiencies depending on where the stations are and where the storms are.
Yeah, so
I
that's
was
definitely.
encouraged that you were going to, with the global lightning on the satellite.
Yeah. Yeah, I think the biggest thing with that is the lightning mapping areas are just so small and in only certain parts of the U.S. And we're trying to get something kind of very large for CONUS wide. So it would be interesting to look at, though, for certain areas.
It'd be interesting just to see if the statistics are consistent, at least in those areas in Colorado, Huntsville, and D.C. at least.
Definitely, yes.
I have one more question, if there's time. I'm wondering if you've looked at the skill for detecting the first lightning strike, because if you're operating a baseball game or at an airport or something, it's also the first lightning strike that is a hazard.
Yeah, we are looking into that right now because yes, it's usually the first and last. I know with airports they want to know when is it done, and then the most important is the first strike. So yeah, we're actually looking at that right now.
Very good.
Well, I guess you got early lunch.
Yeah, thank you. Okay, thank you all.